Good morning, Internet. This is Tobias, DL3MHT, and today's video is literally sponsored by HamRadio dude, W9FFF, who sent me 2 of these nice AIOC boards for analysis. A few weeks ago, the dude suspected some manufacturing problem with the latest batch of AIOC PCBs, and I offered to have a look. So this is what this video is all about. We'll dive into the schematic of the AIOC, see what could go wrong, and then check it out using a multimeter and an oscilloscope. This video will be a bit on the lengthy side, so if you're not interested in my detailed and half-baked explanations, feel free to skip ahead. Okay, so in order to do a sanity check on the AIOC device, we need unfortunately to understand a little bit the schematic. So I printed it out and I have a few marker pens here, and I hope this won't be too boring or won't take too much time. But how would you analyze a circuit that does not work? Well, the first thing you obviously have to check is power supply, yeah? And as this thing is powered via USB, we get our 5 volt here from V-bus coming in here into a voltage regulator. And one important thing to know as well is, as this is USB-C, it is crucial that we have these 2 pull-down resistors here on CC1 and CC2, because as you know, USB-C can provide not only 5 volt but also higher voltages in order to charge devices. And these 2 pull-down resistors, 5.1K on pin CC1 and CC2, basically tell the USB port that this is a, I don't know how I should say, legacy device, so that it switches on the 5 volt power supply. Without these 2 resistors, you won't get 5 volt. Your only chance to get 5 volt is to use a USB-C to USB-A adapter. But if you connect USB-C to USB-C and these 2 pull-down resistors are missing, you don't get the 5 volt. Okay, now we have the 5 volt going into the voltage regulator, and this voltage regulator seems to have 2 different outputs, Vout1, Vout2, which are both 3.3 volt power supply pins. Okay, so we have 3.3 volt twice. Now we need to figure out where that 2 different voltage rails go. I think this one has a little ferrite bead and it says VA, so my guess would be this is audio voltage. So let's see if that is right. So here we have on the microcontroller the STM32F302. We have 2 voltage supplies. So VDDA and VDD, what does it say here, SD, are connected to 3.3 volts, so this one. And probably the digital section is connected here to the digital part of the microcontroller. Okay, so the first thing to do when we do a sanity check on the device would be connect it to a USB port, check the voltage on V-bus, check the 2 3.3 volt voltages at the output of the microcontroller, and then we check if we get these 2 voltages also to the input of the microcontroller. Okay, what would I do next for a sanity check? The next thing that I would do is probably connect a scope somewhere here close to the 8 megahertz crystal oscillator, because if you don't have a clock running, then the microcontroller can't do a lot. So I think somewhere here, I don't know if, yeah, it's probably best to probe somewhere here near to C1 or C2 and connect a scope and see if we can detect here 8 megahertz oscillation. And then I think, in theory, this device, this already gives us a pretty good indication if this thing should work or not. I mean, there's not much else going on here. We have the USB port, we have the power supply, we have the oscillator running. Okay, of course it would be good to know if the USB D plus and D minus pins are also connected to the microcontroller. So we could measure here between A7 and A6 if these if there's a connection with a multimeter, with an ohmmeter, here to PA11 and PA12. But why should there not be? I would probably not check that right now. I would basically power it up, check the voltages, check the oscillation. Okay, any further debugging I would delay until the firmware is loaded. And as you can see here on the output, there's not really a lot going on. I mean, we have here PTT1, PTT2 is just two transistors, NPN I think. Just pull these inputs to ground. So, well, if the transistor is working, there's not much that can go wrong. Then we have the audio input, radio microphone just goes directly here to, no, vice versa. The audio output of the STM goes into the microphone input. And the second pin, what does it say? DAC attenuation. Yeah, I don't know. Maybe you can pull that to ground in order to make the audio output a bit lower volume if you have some issues that your microphone on your handset is so super sensitive that the output on the from the microcontroller is overdriving it. Then maybe you can in software pull that pin and then it lowers the volume towards the radio. So radio mic, this is basically to the radio. And on the other side we obviously have from the radio coming in from the speaker. Yeah, here AF in. So I guess this is the ADC pin probably. You can look in the data sheet. All these pins are probably have different functionalities, and either you can program them as inputs or outputs, or they have additional functionality. It's all in the data sheet of the STM. So I guess here just goes straight in. The audio is here coupled with a capacitor. Since we have our analog voltage at 3.3 volt, this puts it straight into the middle. So 1.6, what is it, 5 volt or something? So that we are here when nothing is going in, we sit straight in the middle of the ADC range, and if we have then audio coming from the radio, we can nicely swing around the center of the ADC. I'm not sure if I'm making sense here. It's probably going already into too much detail, but as you can see, just simply from looking at the parts, there's not much going on, which is good because then there's not much that can go wrong, right? As long as you have your parts here populated, and I mean the PCB is known to work, I don't think the likelihood that something goes wrong here is pretty low. What else do we have? We have a few LEDs. So what's going on here? Okay, well that's interesting. So we have two GPIO pins here used to connect LEDs. So we have a green LED and a red LED. And I don't know what NM is, maybe not populated, or but basically they are connected, the two LEDs are connected anti-parallel. So basically if you give it plus on this side and minus on this side, then the green LED would light up. And if you swap it around, give it plus on the left side and minus on the other side, then the red LED would show up. And how do we do that? Well, probably just two simple GPIO pins, and you program one as a pull down or pull it to ground, and the other one you program it with an internal pull up and pull it high. So by software, basically by controlling these two pins, you can basically decide, does the green one or the red one show up. I don't know why it was done that way. In theory, you could have also just used two separate pins and say, hey, connect the green LED to PB8 and the red one to PB9. But I don't know, what's the benefit here? Maybe, I don't know, you could, of course, blink then alternately red and green. Maybe it depends how the software is written. Maybe it's easier in software than to indicate different operation modes when you hook it up like this. So as you know, we want to probe, let's just number them. We want to probe here, we want to probe V-bus, we want to probe the audio, the analog 3.3 volt supply, we want to probe the digital supply. Obviously, we also want to see, does that voltage end up here on the microcontroller? So I would say somewhere here on C9 or C10. It's probably easiest to connect the probe. We can say this is 2A, and this is here at C7, C8, this is 3A. I'm just numbering the points so that I have it easier afterwards. Okay, what else do we want to do? We measure the oscillator pin. So again, this would be either C1 or C2, doesn't matter which. I guess, I don't know, why not say C1 is our probing point number 4. And in order to program the firmware, we'll have to put a wire bridge between pin 1 and pin 7 of this pin header that is on the PCB. And what that does is, or I assume what it does is, simply apply a 3.3 volt pull up here on boot 0. And this boot 0 pin probably tells the microcontroller if it is pulled down. It probably tells the microcontroller jump to the start of the flash memory where the programmed firmware is. But as we know, we have no firmware programmed in there in the first place. Pulling it up to 3.3 volt probably tells it, hey, execute the internal bootloader, which was put in by the factory. So I assume when this bridge is connected, it will enumerate as some STM flash controller generic bootloader device, and then we can program our software in. And yeah, this is as far as I would take it for the moment. So let's get the inspection microscope out and have a look. Okay, and here we are on the Andon Star inspection microscope. And let me try to get that in focus, which is not so easy because my monitor is 3 meters away. Let me check if that looks sharp enough for you. Yeah, looks good. Okay, so as you can see here, we have the AIOC PCB, and as far as I could see from quick visual inspection, it looks fine. I mean, the soldering joints look okay to me. And what we have to do now is identify our 4 measurement points. We wanted to check V-bus, the 2 3 volt power rails coming out of the voltage regulator, and also well, the 2 3 volt power supply going into the microcontroller, which is this big bug here in the middle. And we wanted to measure the 8 megahertz crystal, which is somewhere here. But since this is a very densely packed PCB, you see there's no markers on the silk screen. Basically, there's no space to put any markers on the silk screen. So what I have to do is take a picture of this and then open the schematics that you can download from I think GitHub or GitLab, or I don't know. Open them with KiCad, and then it is very easy to identify well, which pin is which, because you just hover with the mouse over the PCB layout, and it will tell you, yeah, if you are here, then this is this capacitor, this is this resistor, and so on. And so we basically just have to identify C4, C5, C1, C2, C8, and if we found the right capacitor, then we just have to identify the right side, and then we know where to probe and check the voltages. So not so difficult. Okay, and here we have the result after digging in KiCad. Okay, so here we have the AIOC under the inspection microscope, and I put another camera view here with the multimeter in the top left corner. I hope that is readable. I think it reflects a bit, but that's the best I can do with my flimsy setup here. And now it's time to measure the voltages, right? As you can see, I zoomed in a little bit to be able to better see where I am with my probing points. So here's the USB connector, and you can just hold down with your probe here on the body of the USB-C connector, because that is the ground level. And what you can also see is that my probing tips are not suitable for the job. I need to get finer ones, smaller ones, for being able to safely probe USB pins, because here is the big risk. If you slip and you are somehow measuring plus voltage and then you slip and short out some pin here, there's a chance that you might, in quotes, well, or not in quotes, you might damage your microcontroller. So this is probably the dangerous bit of the operation, not trying to kill the electronics that you try to debug by slipping with your probe leads or probing equipment. So let me try to hold this down here now. With the right hand, I'm holding the ground pin to the body of the USB connector. And now we want to see, do we have V-bus here? Do we have the plus 5 volt from the USB port? And this is the ferrite bead that comes out, and then the plus 5 volt go into the voltage regulator. So on either side of this, we should see 5 volt. And if I try to probe on the right side, I have to be really careful to not short out here to ground. So maybe take a breath and try it slowly. 5.17, I hope you can see that on a multimeter. So we have the plus 5 volt power supply, that's good. Now we have to check the output of the voltage regulator. So there's the digital voltage coming out here and is available here on the left side of that capacitor. Let's again try to not cause a short. That's really not good. I really need to get finer probes. .29, okay, I think you saw it. And then the other output, the analog 3.3 volt supply voltage for the ADC and the DUC comes here. So on either side of that ferrite bead we should be able to measure 3.3 volt as well. So let's try that. That one's a bit easier. Now my multimeter wants to go into power down mode, but I stopped it. So 3.288. Okay, so that means 5 volt in, 2 times 3.3 volt out. That's already promising. And now what we could do is on the filtering capacitors that are sprinkled here around our microcontroller, I could just also measure that we have the voltage. So I think, let me have a look. Where is the digital supply voltage? I think this capacitor here. Again, a tricky one because we are close to some pins. Here on the right side we should see 3.3 volt. 3.291. And then at the, let me have a look, at the bottom part there's a bigger one, maybe a few microfarad. So that's the other one. Oops, I need to sneak around the light and not short out. 3.29 volt, I think you saw it. Okay, so now the analog supply voltage. There's a capacitor here on this one here. Oops, I have to move it a bit so that you can see it. .287, I think we saw it, but I'm sliding off. Now you saw it. Okay, and on the other side we have again a bigger one. Here, this one should also be 3.3 volt. Oops, I think you saw it. 3.287. Okay, so what have we seen? All supply voltages for the microcontroller are there. Okay, so I've set up the scope and I try to probe the oscillator, which is this bit here on the left and on the right side, or here in between the two coupling 22 picofarad capacitor that go to ground. But I'm not getting any signal, and I'm wondering if that is because the firmware is not yet programmed, because some of these microcontrollers have an internal oscillator and an external oscillator. So I'm not sure if I am supposed to see an oscillation already. I think what I will try next is hook up the two connectors here to get it into bootloader mode and see if I get anything on the computer, if it enumerates as some USB device or not. Okay, so now we are ready to test the AIOC device. As you can see, I have a nice jumper cable soldered here to get it into bootloader mode. And here's the other end, and I will switch over to the monitor view like this and insert the cable, and then we see if bootloader shows up or not. And hooray, something happened. The device manager was flickering, and indeed, here we have the STM32 bootloader. So let me switch again. So as far as I could see, this device might actually work fine. I have to flash the firmware.
1 hour later.
Okay, firmware is flashed successfully. We have a green light here on the PCB. The bootloader device has disappeared from the device manager, but we have a AIOC DFU runtime device with a missing driver. Not sure if that's normal. And we have a AIOC audio speaker and AIOC audio microphone. And in theory, we should also have an additional UART, which is probably this one. sure if I can detect that. But maybe if I pull the plug and it disappears, we know it's it's this UART. Let's try that. And something has happened. Yeah, it's disappeared. So that it was that UART. Yeah, so flashing the firmware has worked. And now let's check the oscillator output. And let me just plug in the USB, and you already see the difference. Okay, as you can see, the red and the green LEDs are working now. And surprise, surprise, we can now also measure the 8 MHz oscillator. Again, ground connection on the body of the USB port, and put my scope probe here. And as you can see on the Rigol, lovely sine wave. So I was right. Without the firmware loaded, it was not using the external oscillator, which can of course be a trap when you're debugging some hardware. You have to know if the firmware is already loaded and how it is using the surrounding hardware. As you saw, there was nothing wrong with the AIOC board. Everything worked perfectly, and shortly after the dude had put these devices into the post on their way to Germany, he figured out that the problem was in fact on the other end of the USB cable. One of the USB ports on his PC or laptop had died, sending him on a wild goose chase. I hope this video was useful for him and for you. Again, I'm just a hobbyist that does not know what he's doing 90% of all times, but some basic electronics problem-solving skills is something that every ham can acquire. Don't try any of this on your most precious and expensive possessions, and when it comes to AC mains voltage, I stay far away from it unless I know exactly what I'm doing. As Zero Brain, a German YouTuber, has put it so succinctly, electricity can kill you deadly. Thanks for watching, and until next time, bye!